2018 number 4 here. So it says the height of the tree at time t is given by twice differentiable function here, h. And then we have table over here, as you can see. Now t is in years, measured in years. And then h obviously is in meters here, as you can see. Use the data in the table above, estimate h prime of 6. So when you look into that, we don't have 6. 6 should have been right over here. Then how can you approximate the derivative of 6? Oh, okay, we're going to be using the value around it. So to show the solution A, h prime of 6 can be expressed as an average rate of change between 5 and 7. So we're going to get h of 7 minus h of 5 over 7 minus 5. Now then you can see that the values would have been h of 7, which is equal to 11. H of 5 is equal to 6 minus 6 over 2. So we get 5 over 2. That would have been the value. Now, what would be the unit? This would be how much it is changing. So it's the rate rate of change in height of the tree. The tree is 5 over 2 meters per year. So that's how much it's basically growing. When t is equal to 6 years. All right, explain why there must be at least one time from 2 to 10 where h prime is equal to 2. Now, this one looks like a mean value theorem, as in there must be h prime, which means the instantaneous rate of change, where which is equal to the average rate of change. Because this one is, first of all, continuous and twice differentiable function. To write down the solution for B, I'm going to write them right over here. Since h of t is continuous and differentiable, mean value theorem can be applied. So we need to state that one first. Now, then when you look into this one, we are looking for a section where slope is equal to 2. So first, since they gave us 2 and 10, I'm looking at these two. I'm trying to find the slope here. 15 minus 1.5 over 8 minus 2. Is that slope looks like a 2? This is about 13.5 over 8. No, that's not it. So I'm going to erase that. That's not going to work. Is there any other values where the slope is equal to 2? Between these two, increase of 0.5 and the increase of 1, no, increase of 4. Oh yeah, how about this one? These two sets of values. This is 6 minus 2 over 5 minus 3. That is in fact equal to 2 because 5 over 3. And these two values are from 5 and 3. So we realize that h of 5 minus h of 3 over 5 minus 3. So we realize that by mean value theorem, there is C, where h prime of C is equal to 2, where C is greater than 3 and then less than 5. that's what we can write. Now, part C uses trapezoidal sum with 4 subinterval approximate the height of from 0 to 10. If you want to use the trapezoidal rule, let's see. First interval would have been this one, second, third, fourth. But you can see that our bases are not the same, so we actually have to calculate each one. And then they're saying average height. Average height is found by integral of h of t dt from 2 to 10, but divide by 8, because 8 is the difference between those two intervals. So I'm going to have 1/8 to begin with, but the integral can be expressed using the trapezoidal sum. So how are you going to find it? Formula is 1/2 base 1 plus base 2, so 2 plus 1.5, and then add 1 to it. So then, that's basically what we end up getting. So we get 1/2 2 plus 1.5 times by 1, because 1 is the height or difference in t values, plus, but the thing is, you'll realize that everything has 1/2 in it, so I'm going to put another parentheses here, bracket, to incorporate all the 1/2s together for the trapezoidal rule. And next one is between these two, so we get 6 plus 2, and then times by 2, times 1/2. Now, next one is these two, we get 11 plus 6 times by 2. Next will be 15 plus 11 times by 3. Now, so then let's try to calculate this one. Whoosh. So then you can see that we have 1/16 in the front. And then you're going to add up all these values. So this becomes 3.5. And then this one is 8 times 16. And then we're going to be adding, this is 17, so plus 34. So far we get 53.3. And then this one is 26 times 3. So we get 78. So 131.5. So we get 131.5. So that's basically what we end up getting. So average height in this case, average height would have been, if I had to write down the answer, 263 rather, over 32 meters would have been the average height. All right, let's look at part D. Now, height of the trees can be also modeled by this way, okay? Where G is the diameter, X is the diameter of the base, and then when tree is 50 meters tall, okay, 50 is here, the diameter of the base is increasing. So that means X is increasing at this rate. Now, according to this model, what is the rate of the change of the height? So then, basically, this is a related rates question. So then first, what we want to do is we want to calculate the derivative here. Then we get dg dt will be equal to, I'm going to take the derivative of this one. Since it's a fraction, I'm going to use the quotient rule. Denominator has been squared. Derivative of the top, which is 100, times the denominator, plus top not plus, rather minus, top times the derivative of the bottom, which is equal to 1. Then you get to realize, and then multiply that by dx dt, by the chain rule. Then what we end up getting here is 100x cancels away, so we have 100 over 1 plus x squared times dx dt. And then what they said was when tree was 50 meters tall. So what does that mean by a tree was 50 meters tall? Then I'm going to figure that out from original function. 50 equals 100 over 1 plus x, 100x rather. And then we get 50 plus 50x plus 100x. And we get 50x equals 50, hence x equals 1. Okay. When the tree was 50 meters tall, x was equal to 1. That's what we get to realize. Then, in this case, when x equals 1, I'm going to place 1 here. So then we get 100 over 4, because 1 has to be squared. And dx dt was 0.03. Then we get 3 over 4. That's basically what we end up getting. That means the tree is growing 3 over 4 meters per year when it is 50 meters tall. All right, so that's basically how we can do this one question. All right, I'll see you later. Bye-bye.